In year 12, you met 4 different types of substances: the metals or metallic substances, ionic substances, molecular substances, and the covalent networks. Each of those had characteristic properties, and you could explain those using the types of particles that they were made up of, and these are shown here, and the types of forces between those particles, again shown here. In year 13, we just take this a little bit further and we really focus on the ionic compounds and the molecular compounds. We don't worry so much about the metallics or the covalent networks. You do still need to remember that these are cations and a sea of valence electrons, and that attraction is called a metallic bond. You do still need to remember that covalent networks are atoms bound in a 2D if it's graphite, 3D and other things like diamond, lattice, and those atoms are held together by covalent bonds, because these two things here do help you explain their melting points, boiling points, and, well, solubility is a bit of a moot point because neither is soluble. So the strength and the 3D nature of these, you still do need to remember. However, we really focus on these two here. There is a fifth, of course, and that's our noble gases, and they are just atoms. They're gases because they have extremely low melting points and boiling points. However, we can cool them enough to turn them into liquids or solids. So therefore there must be some potential forces between the particles. We call those van der Waals forces or London dispersion forces. They are the same name, different names for the same thing. Basically, they are where the electrons are not evenly distributed around the atom, so allowing for an attraction between each atom because of that uneven distribution of electrons. We'll explore that more when we look at molecules, because a similar thing happens with what's called a temporary dipole. The larger the electron cloud in an atom, the higher its melting and boiling point will be, because the larger the electron cloud, the more unevenly distributed those, particularly valence electrons, are going to be. If you think of a classroom, if it's a very large classroom, then you can distribute students that in a variety of ways, and they're unlikely to be even. Whereas if you have a much smaller classroom with fewer seats, for example, so therefore a smaller electron cloud, to fit the same number of students in, they're going to be more evenly distributed and probably a lot closer together. That's sort of an analogy for how van der Waals works. We don't focus on these a lot, but it's good for you to know that name to help explain how atoms bond together when they get cool enough to be liquids or solids. So our first one we're really going to focus on is our ionic compounds. Different ionic compounds have got different melting points and boiling points. Some of them are much more soluble than others, which you might remember from last year, where some ionic compounds were classed as insoluble, which means they had incredibly low solubility, while others were said to be soluble. What makes these differences? They're all made up of cations, they're all made up of anions, they're all in 3D lattices, and they're all held together by very strong ionic bonds. So why these differences? We're going to explore how the ionic radius and the ionic charge influence melting point, boiling point, and solubility, particularly in water. We're then going to go on and look at molecules, and I've tried to do a simple diagram of a polar molecule here with a slightly positive and a slightly negative side, and an intermolecular force between them called an intermolecular bond. We've learned that molecules can be non-polar or polar, and we can determine that from their shape and from their electron cloud to see if there is any asymmetry in their electron distribution. Non-polar molecules should not bond together. They should be just like atoms, but they do. And we know that some non-polar molecules are solid at room temperature. For example, iodine. For example, your very large hydrocarbons. So with about 15 carbon atoms, an alkane, or so it'd be C15H32, would be solid. So it's wax, basically. We know they're solid, so they must have forces between them. Well, what happens is, in a non-polar substance, these dipoles get formed temporarily and just long enough to create temporary dipole forces. So they have a force with the neighbouring molecule, even though for the majority of time they're both non-polar. For a moment in time, they're polar temporarily. And we're going to explore the formation of temporary dipoles. Now, the larger the electron cloud, the more likely these are to occur. Therefore, the larger the molecule, the higher these things are going to be. We call temporary dipole forces intermolecular forces, a word we learnt last year. And they help us explain why non-polar substances can be, for example, solid or liquid at room temperature. These forces do exist between them even when they're non-polar molecules. The other one is the polar molecule. Now, polar molecules have a permanent dipole. This end is always delta positive and this end is always delta negative, for example. So when they come near another molecule like that, of course an electric attraction is going to form. And this is called a permanent dipole force. Again, this is an example of an intermolecular bond. Now, there is an extreme case. Something like water should be a gas at room temperature. The molecule is so small, even though it's polar, it shouldn't be a liquid at room temperature. It should be a gas. But it has a special type of intermolecular bond called a hydrogen bond. And we're going to spend a lesson looking at those as well, because they are a very, very important explanation for why certain compounds have got unusually high melting points and boiling points, and why they can form such strong relationships with other molecules that can do hydrogen bonds like water, so therefore it also affects their solubility. So there we are. There is an overview of where the learning is going. These four are a recap of last year, but we're going to take them deeper using our knowledge of atomic structure, ionic radius, our knowledge of molecular shape and polarity, to explain some physical properties, particularly melting point, boiling point, and solubility, because they link to the strength of these forces between the particles.